Okay, so starting over with this problem since the mistake was made, we have the first ball is moving at the first ball is 2.5 kilograms and it's moving at 1.7 meters per second. So this arrow represents not the velocity vector, but the momentum vector. And I can figure that number out simply by multiplying 2.5 times 1.7. That's going to be the value. So I actually know what the value of that is. I'm also making it so that it goes in the x direction so that all my momentum before collision is in the x direction. So it says that the first ball, so this ball right here, moves off in a direction of 26.6 degrees to the right of its original direction. So like I was saying before, if I wanted to go to the left, then I would have it where it's going to hit above the equator. That would send this ball that way. If I want this thing to go that way, then I'm going to have the other ball so that it's going to hit below the equator of this. If I put it right there, it's just going to go in a straight line, and we're not going to have a collision at an angle. So I need this one to go that way. So for this one to go that way, I need the ball, the second ball, to be right there so that it hits above. That's not a very good circle, but that's the ball. And the angles after the collision are all going to be based on the original direction of the first ball, which was the x direction. So I want to extend that to the right. So that's the original direction of the first ball. If it didn't hit the second ball, that's the direction that it would have gone. So it says, after the collision, the first ball moves off in a direction 26.6 degrees to the right of its original direction. So 26.6 to the right would be in this direction. And I'm going to make it about this size. And so what I just drew there, that is the momentum of the first ball after the collision, and that angle right there is 26.6 degrees. Now the second ball also goes into motion when it gets hit by the first ball. And it says that the second ball moves off in a direction 10.8 degrees to the left of the first ball's original direction. So that means that the second ball, 10.8 degrees, is a smaller angle than 26. So I'm going to be going like this. And watch how far I go. I'm going to go right about there. And the reason why I made it that long is because I know that before collision, all the momentum was in the x direction. So after collision, all the momentum has to be in the x direction. So any y components have to cancel out. So I drew this line long enough so that the distance from there to its original path and the distance there was the same thing. So that length right there is going to be the same as that length right there so that they cancel out. Because if I had no momentum in the y direction before collision, I can have no momentum in the y direction after collision in total. So I'm going to label this also as this is the momentum of the second ball after collision. And I'll put in the value, that's 10.8 degrees. So one thing that I didn't really draw to scale, because I did make this one too long. Even at that length, I made it too long. So I had to go all the way out here to make that. Well, the x component of this one is that length right there. That's the x component of this one. This is the x component of that one. So this one has an x component and a y. This one has an x component and a y. Well, if I add up that distance and that distance for a length, it should be equal to that, and I think this is shorter than what those two would be if I added them together. But you don't need to be that exact. as long as you can read everything off the picture to come up with your momentum equations. So once I have the picture, the next thing I'm going to do is I'm going to sum up my momentums in the x direction. Now I know yesterday I think I just wrote x, but when we did forces, we wrote some of the forces in the x direction, some of the forces in the y. So we are doing momentum, so I'm going to use in parentheses that. So my equation in the x direction, before collision, the momentum is just P1. Now, since I'm not labeling a vector, I'm just putting the value P1 in there. After collision, if you look at it after collision, again, this is the x component of that one, and that is the x component of that one. Both of those are what side of my triangle? So this and then that. What is this side? Is that the opposite side or the adjacent? Adjacent. So when it's adjacent and we're solving for a component that's the adjacent side, what trig function do we use? Cosine. So we use cosine, so it's going to be, the bottom one there is going to be P1 prime times the cosine of 26.6 degrees. All right, and it's positive because that component is to the right. Then to that, we're going to add because the component of the other one is also to the right. So it's going to be P2 prime times the cosine of 10.8 degrees. So that's my momentum equation in the x direction. Now in the y direction, when I sum up my momentums in the y direction, before the collision, there was no momentum in the y direction, so the whole left side is 0. And when I sum up my momentums on the right, the P2 prime is the one that has the positive y component, so that's going to be P2 prime times, if the other one was cosine, then this one's going to be what? Sine, because this side over here is the opposite side from that angle. So, and this one, that's the opposite side. So the y components are both opposites for both of these. So that's going to be P2 prime times the sine of 10.8 degrees. And that's positive because that component for P2 prime is up. But the other one is down. So this one is I go to the right and up, and for this one I go to the right and down. So since I'm going down, it's going to be minus P1 prime times the sine of 26.6 degrees. And I know I've told you not to put the values in until the end when you're doing algebra, but in a problem with angles, it's probably easier just put the angle in because I can just as easily call that theta 1 and theta 2 as whatever the value is. It's not going to change my algebra in working this out. So I would do that. So just put the angle values in. Now that I have this, I have two unknown variables, but I've got two equations with the same two unknown. This is not an unknown because they gave me the mass of ball 1 and they gave me the velocity, so I can figure that out. So that's not an unknown. But that's an unknown, and P1 prime and P2 prime are unknowns. So in order to solve when I have two equations and two unknowns, I'm going to use the second equation to create a substitution and put that into the first equation. So P2 prime, I'll solve for P2 prime here. So P2 prime is going to equal P1 prime sine of 26.6 degrees divided by the sine of 10.8 degrees. All I did was algebra here. I moved this thing to the other side, and then to get P2 prime by itself, I divided by sine of 10.8. So this right here is now my substitution. I can now take this and plug it in right there, and then I'll have only P1 prime in that first equation. So this right here is now going to be put in right there, And the rest of the problem is algebra. We're done with the physics. So taking that first equation, and we haven't solved a P, well, I'll wait till the end. So, because I can even replace this with, M1, V1 when I plug in, because I know what M1 is and I know what V1 is. But right now I'm going to plug into that equation. So I'm going to get P1 is going to equal P1 prime cosine of 26.6 degrees plus, and now I'm going to replace P2 prime. I'm going to replace P2 prime with that. So that's going to go in there, and then I'm going to put the cosine of 10.8 on the outside. So cosine of 10.8 is going to be there, and then I'm going to put in P1 prime sine of 26.6 degrees divided by the sine of 10.8 degrees. And I'm over 11 minutes now in solving this problem, so I've got to be careful that I don't run over 15 minutes. I'll have to stop it even if I'm not finished. So the next step is, algebraically, the next step is if the equation contains fractions, you multiply by the least common denominator. And the least common denominator is the only denominator here, which is the sine of 10.8. So that means that each term has to get multiplied by the sine of 10.8. And when I do that, I'm going to get P1 times the sine of 10.8 equals P1 prime times the cosine of 26.6 degrees sine of 10.8 plus, now the third term, see there were three terms here. So this term got multiplied by the sine of 10.8, this term got multiplied by the sine of 10.8, and now here's the third term. The reason why I'm multiplying by the sine of 10.8 is so that cancels out with that. And so I'm just going to be left with the top. So that's going to be P1 prime sine of 26.6 degrees cosine of 10.8 degrees. Now, I want P1 prime, that's my unknown, so I'm going to notice that I have the unknown in both of these terms. So I can factor it out, and when I factor this out, what's going to be left is these trig functions plus those trig functions. And then that will eventually come down here below. So I'm running out of time. Well, I still got 2 minutes, so let's see if I can do at least the next step. So when I've done that, what I'm going to get is that P1 prime is going to equal this, which is already on the other side. So I'm keeping this there, even though I put it on the left. That's on this side. So I'm going to have P1 sine of 10.8 degrees divided by, and now what it's going to be divided by is when I pull out the P1 prime, I'm going to have that plus that. And so that's going to end up being in the denominator down here. So that's going to be the cosine of 26.6 degrees sine of 10.8 degrees plus sine of 26.6 degrees, cosine of 10.8 degrees. Extend that line. And so plugging that in, you'll get the value for P1 prime. Once you have that answer, because I now have to talk out the rest of this because I'm going to run out of time. Once you have that answer for P1 prime, I can then take that answer and put it in here, and then I'll have P2 prime. And if I have both of these, then I can solve for each of their velocities because I know the mass of each one, so I could then solve for their velocities.